Welcome to this chapter on AI for progress tracking and project controls. In the previous chapter, we focused on how AI can support pre-construction, estimating, and scheduling before the baseline plan is finalized. Now, we move into the construction phase, where project teams must continuously understand three things: what has already happened, what is happening right now, and what is likely to happen next. Traditional project controls are essential, but they often face several limitations. First, many systems are reactive. They work almost like a thermostat. The team measures performance, compares it with the plan, identifies a variance, and then responds. The problem is that by the time the delay is visible, it has often already affected the schedule. Second, progress reporting can be subjective. A subcontractor may report that an activity is 80% complete for several weeks, even though the remaining work is blocked by coordination issues or missing information. Third, construction data is often fragmented. Schedules may be in Primavera P6, design data may be in BIM, cost information may be in an ERP system, and field updates may be stored in separate mobile apps. When these systems do not communicate well, managers spend too much time reconciling data instead of making decisions. Finally, small delays can remain hidden until they create larger impacts. A minor delay in one trade can affect inspections, downstream work, material deliveries, and project turnover. This is where AI can add value. The goal is not to replace project managers, superintendents, schedulers, or cost engineers. The goal is to reduce the time between field reality and management response. One of the most important ways AI supports project controls is through computer vision and reality capture. Computer vision allows computers to interpret information from images, videos, scans, and other visual records. In construction, this means that visual field data can be transformed into measurable progress information. Reality capture is the process of regularly digitizing the physical job site. Several technologies can support this process. 360-degree cameras can be used during routine site walks to create time-stamped room-by-room records of work in place. Drones can document exterior progress, earthwork, stockpiles, logistics areas, and locations that are difficult or unsafe to access. Autonomous ground robots can follow repeatable routes and collect consistent interior data from one reporting period to the next. LiDAR scanners and laser scanning systems can create point clouds that compare the physical job site with the planned digital model. Once this visual data is collected, AI algorithms can process it. These algorithms can detect objects, classify components, and identify installed work. For example, AI models may recognize walls, columns, equipment, materials, or MEP components in field images. The key value for project controls is that unstructured visual data does not remain only as photos in a project folder. Instead, it becomes structured, machine-readable progress information that can be connected to the schedule and cost control systems. The value of AI becomes even clearer when computer vision and reality capture are connected with BIM. This enables automated installed quantity tracking. In a traditional process, the team may rely on a superintendent's estimate or a subcontractor's progress report. But with AI-supported tracking, the system compares the captured field condition with the planned digital model. The as-built condition is collected through cameras, drones, scanners, or robots. The as-designed condition comes from the BIM model. When these sources are aligned, AI can identify whether specific building elements are present, partially installed, missing, or different from what was expected. This allows project teams to measure installed quantities more objectively. For example, instead of saying that second floor framing is about halfway done, a dashboard may show that 54% of the steel stud linear footage has been visually confirmed as installed. This type of measurement reduces subjectivity. It also helps owners, general contractors, and subcontractors work from a more consistent source of truth. However, there is an important distinction. Visible progress is not the same as final acceptance. A component may appear to be installed, but it may still need inspection, testing, commissioning, documentation, or quality approval. So, progress tracking answers one question: how much work appears to be installed? Quality inspection answers another question: is the work correct, compliant, and ready for acceptance? AI can support both processes, but they should not be treated as the same thing. Another major benefit of AI in project controls is the ability to identify early warning indicators. Traditional controls often rely on lagging indicators. These tell us what has already happened. For example, a schedule update may show that an activity is already behind, but by then, the delay may already be affecting the critical path. AI helps shift project controls toward leading indicators. These are early signals that a delay or productivity problem may occur. First, AI can support predictive analytics. Machine learning models can analyze weather forecasts, productivity trends, supply chain information, schedule updates, daily reports, and field imagery. Models such as gradient boosting and random forests can detect patterns across many types of project data and forecast where the project may drift from the plan. For example, if the schedule requires a crew to install 500 square feet of formwork per day, but the actual production rate is averaging only 350 square feet per day, the system does not need to wait for the milestone to be missed. It can project the trend forward and warn the project manager early. Second, AI can support benchmarking. It can compare an active project schedule with historical project data. If similar projects usually required 6 weeks for a complex MEP coordination phase, but the current schedule allows only 4 weeks, the system can flag that activity as high risk. Third, AI can support what-if optioneering. When a disruption occurs, the team can test recovery strategies such as weekend shifts, additional crews, resequencing, overtime, or alternative delivery plans. The value of AI is not just that it identifies a problem. The real value is that it helps the project team evaluate recovery options while there is still time to act. The long-term goal of AI in project controls is to connect field progress, schedule logic, and cost information into one dynamic management system. This is where the concept of a digital twin becomes important. A digital twin is a live virtual representation of the physical project. It can combine BIM data, schedule logic, cost codes, equipment information, and reality capture records. Unlike a static BIM model, a digital twin is connected to current project conditions. This makes it useful for tracking progress, forecasting cost exposure, evaluating schedule alternatives, and communicating project status. AI can also strengthen earned value management, or EVM. Traditionally, EVM connects scope, schedule, and cost, but it often depends on manual progress reporting. Because of this, metrics such as the Schedule Performance Index and Cost Performance Index may be updated only after progress information has been collected and verified. When AI-supported computer vision confirms installed quantities, that progress data can feed into EVM calculations after proper review. AI can then help forecast final cost and completion dates based on current production rates, labor hours, installed quantities, procurement status, and changes. AI can also reduce administrative work. Natural language processing can summarize field reports, connect observations to schedule activities or cost codes, and help prepare progress summaries, payment applications, or compliance documentation. The system does not approve payments or make management decisions by itself. Instead, it gives the project team more current and better organized evidence for decision making. Equipment performance is also an important part of project controls. Heavy equipment failures can stop critical activities, delay material movement, increase standby time, and create unplanned repair costs. For that reason, equipment data should not be treated as a separate maintenance issue. It should be part of the project controls information system. Telematics and sensors can track engine hours, idle time, fuel consumption, vibration, hydraulic pressure, temperature, location, and fault codes. AI can analyze these signals to identify abnormal patterns before equipment fails. For example, a crane, excavator, loader, or concrete pump may begin showing unusual vibration, heat, or operating cycles before a breakdown occurs. If the system detects the problem early, maintenance can be scheduled during a planned shutdown rather than during a critical path activity. AI can also support productivity analysis. If an excavator is assigned to earthwork but spends much of the day idling, the issue may not be the machine itself. It may be a truck cycle problem, a haul route issue, poor sequencing, site congestion, or a crew balance problem. When equipment data is connected to schedule activities and production targets, managers can better understand the source of productivity loss. Predictive maintenance is not only a technology function, it is a management practice that helps protect the schedule, reduce unplanned downtime, improve resource planning, and support safer field operations. Let's close this chapter with a case study concept: predictive project controls on large urban construction projects. Large urban projects often involve dense site conditions, overlapping subcontractor schedules, limited laydown space, strict milestone requirements, and complex logistics. In this environment, small delays can quickly create larger problems. A delay in one work area may affect crane time, material deliveries, inspections, crew access, and downstream trades. If the project team discovers the problem only during a weekly schedule update or a monthly progress meeting, the response window may already be too short. AI-supported project controls help shorten that response window. They combine field data, schedule logic, productivity trends, weather data, and historical project information to provide earlier warnings. For example, the system may compare actual production rates with planned production rates by trade, zone, or work package. If drywall installation, MEP rough-in, or facade installation begins to fall behind the expected productivity rate, the system can alert the team before a major milestone is missed. The team can then test recovery options. They may resequence work areas, adjust crew allocation, revise delivery timing, add shifts, or change equipment use. The broader lesson is that AI in project controls is not simply a technology add-on, it is a management strategy. The final decision still belongs to the project team, but with AI-supported controls, the team can make that decision with better evidence, earlier warnings, and more time to respond.